Hey guys, and welcome back, and this week's video is going to be about oxidation states, so chemistry focused. So first of all, what is an oxidation state? Well, an oxidation state or number is basically just a number that represents the number of electrons transferred, so lost, gained, or shared by an atom. So for example, if there's a compound that is formed in ionic, then the more electronegative element will have gained electrons, and those would be the oxidation state. Another example is that the oxidation of calcium is always +2, and that's because calcium always loses 2 of its electrons and becomes a positive ion. So what is the format for oxidation states? Well, basically you have your element, for example E right here, and the oxidation state has its sign, so positive or negative, before its value. So like we've seen before, calcium +2, magnesium +2, chlorine -1, and so on. So it kind of goes in the opposite of the charge because, for example, the charge of calcium is 2+, but oxidation state is +2. Now there are a couple of rules, so to speak, with oxidation states that make sense, but this is just them being formatted as rules. They're actually very logical. So first of all, if an element is pure, then the oxidation state is 0. And this makes complete sense because the electrons are right in the middle, so there is no really transfer of any electrons. For example, in oxygen, if we have 1, 2, 3, 4, 5, 6, and another oxygen, 1, 2, 3, 4, 5, 6, these electrons are right in the middle, so no electron is getting pulled over to one side or another, and there is no oxidation state for either of these. Now, if we have an ionic compound, then this is quite intuitive. The oxidation state is just the charge of each ion. So, for example, again, if we have calcium chloride, then this calcium will have an oxidation state of +2 because the calcium ion has a charge of 2+, and the chlorine, each chlorine, will have an oxidation state of -1 because each chlorine ion has a single negative charge. And just pointing out that despite there being 2 chlorines, we still write the oxidation state for just one. Now, a bit more complex are the covalent compounds, and in this case, if we focus on carbon tetrachloride, we first figure out how many electrons are there, how many electrons are shared, and each carbon is sharing 4 electrons, and each chlorine is sharing 1 electron, and this is our number. But to find out the sign, we have to focus on the electronegativity of each element, and the more electronegative element gets the negative sign. And this makes sense because the more electronegative element attracts the electrons closer to itself, and it's going to have a more negative charge on it. And so in this case, the electronegativity of chlorine is greater than the electronegativity of carbon. So we're going to have carbon having an oxidation state of +4, and each chlorine having an oxidation state of -1. Now, a way to check your oxidation states is by knowing that in a neutral compound, the oxidation states add up to 0. If we go back to this example, where we have carbon tetrachloride, and carbon has an oxidation state of +4, and each chloride has an oxidation state of -1, we have 1 carbon, so 1 + 4, and then +4 times -1, which is going to be 4 - 4, which is 0. So again, we see that in a neutral compound, our oxidation states will always add up to 0. Now think about what would happen if we had oxidation state of a polyatomic ion. If they add up to 0 in neutral compounds, then they would add up to the charge of the ion in polyatomic ions. And for example, let's take OH minus. This should add up to -1. And an O always has an oxidation state of -2, right? Because it's giving 2 electrons. And an H has an oxidation state of +1 because it's attracting 1 electron to itself. So our oxidation state is going to be -2 plus plus 1, which is equal to negative 1, which is equals to the charge of OH, or polyatomic ion. Another example will be carbonate, so CO3, 2 minus. And in this case, carbon again has an oxidation state of plus 4, and oxygen, each oxygen has an oxidation state of minus 2. And if we add that together, we're going to have 1 plus 4 plus 3 times negative 2. So we're going to have 4 minus 6 is equal to negative 2. And this is equal to the charge of carbonate. Okay, now let's move on to some exceptions or some specific examples. And one that I would like to look at is peroxide. So before, when we looked at oxygen, oxygen always had an oxidation state of negative 2. And this is pretty obvious because it always needs to gain 2 electrons in order to have a full valence shell. But in peroxides, and a peroxide is a chemical compound where 2 oxygen atoms are linked together by a single bond. In peroxides, the oxidation state of oxygen is going to be negative 1. So for example, if we have hydrogen peroxide, which is H2O2, we know that this is neutral, and we know that hydrogen always has a plus 1, and the only way that this works is that oxygen has to have a minus 1 instead of a minus 2. So just remember that if you have a peroxide, the oxidation state of oxygen will be negative 1 and not negative 2. Another exception is with hydrides, and this one is for hydrogen. Usually hydrogen has an oxidation state of plus 1. And this makes sense. Hydrogen needs to gain an electron, but it's very weak in its electronegativity, so it always ends up kind of sharing it more towards the other side, gaining it a more positive charge. But hydrides is when hydrogen is bound to metals. Metals have an electronegativity even lower than hydrogen, so in hydrides, the oxidation state of hydrogen is going to be not plus 1, but negative 1, because the electrons actually move towards the hydrogen. So for example, if we have sodium hydride, which is NaH, sodium will always have a plus 1, and this makes it only possible for hydrogen to have a negative 1 oxidation state. So these are the rules. They're pretty straightforward, and they make sense, especially just take a little moment for it to sink in, because they're all very logical and very intuitive. For example, the most intuitive I find is the ionic compounds, because oxidation state is basically just the charge, which makes complete sense because the oxidation state represents the number of electrons gained or lost or shared in covalent compounds. Now, another way that we can use oxidation states is to find oxidation states of elements that have variable oxidation states. So for example, nonmetals have various oxidation states, and we indicate each oxidation state with a Roman numeral. So we can look at sodium chlorides, and there are a lot of possibilities of sodium chlorides. For example, we have NaClO, we can have NaClO2, we can have NaClO3, and we can have NaClO4. And think back to the previous slides. We know that oxygen always has an oxidation state of -2 unless it's in a peroxide, but none of these are peroxides. And we also know that whenever there's somewhat of an ionic compound, the ion will have its own charge, and in this case, the ionic compound is between chlorate and sodium, so sodium will always have a +1 charge. And the only thing that is left is chlorine. So we know that chlorine here has this variable oxidation state. And how we find this oxidation state is by knowing that overall this compound is neutral, so all of the states have to add up to 0. So we can create a little equation that +1 plus X, and let's say that X is the oxidation state of chlorine, -2 is equal to 0. Well, that means that X is equal to 1. And that means that the oxidation state of chlorine is +1. So in this case, we would denote this as sodium chlorate with a 1 in the Roman numeral. In this case, we're going to have +1 plus x minus 2 times 2 is equal to 0. And now we're going to have that x minus 4 plus 1 is equal to 0. So x is equal to +3. So our chlorine here is going to have an oxidation state of +3. Now let's look at the example below. Here it gets even wilder. We're going to have a +1 plus x plus 3 times -2 is equal to 0. We're going to have that x minus 5 is equal to 0. So x is going to be equal to +5, and the oxidation state of chlorine is going to be +5. And lastly, we're going to have +1 plus x plus 4 times -2 is equal to 0. So x is going to equal to +7, and our oxidation state of chlorine is going to be +7. So here we would denote this as sodium chlorate with 3 in the Roman numerals. This would be sodium chlorate with a 5 in the Roman numeral, and this would be sodium chlorate with a 7 in the Roman numeral. And here we can see how all of these different compounds are still sodium chlorates, but in each one, the chlorine has a different oxidation state. So I hope you enjoyed, I hope you find this useful, and I hope you are more familiar with oxidation states and what they are. See you next week.